Welcome to the deep dive. We take the sources you're curious about, pull out the key insights, and basically make you instantly smarter.
Yeah, it's all about getting straight to the good stuff.
Exactly. And today, we're plunging into the world of deep learning. This is all based on material you provided, specifically the book Deep Learning with Python.
Great source.
Yeah.
Very influential.
Right. So our mission here is simple. Give you a clear, engaging, and maybe even surprising understanding of what deep learning actually is, how it works under the hood, and, why it matters so much right now, all without the confusing tech speak.
Yeah, we'll try to keep the jargon to a minimum. And remember, these deep dives can come from anywhere. Articles, research, your own notes. Doesn't matter.
The goal is just solid knowledge, fast but thorough.
Okay, so to kick things off, what is deep learning? Like, what's the big picture?
Good question. When we say deep learning, what are we really talking about?
Well, at its core, it's about getting computers to do tasks that normally require human intelligence. It's a branch of artificial intelligence, AI. But AI is a huge field, right? It includes lots of stuff that doesn't involve learning at all. Think back to, like, the old symbolic AI.
Ah, the rule-based systems.
Exactly. People programmed in tons of explicit rules, like, if you see this, then do that. And, that worked okay for really structured problems. Perfect game of checkers, maybe.
But not for the real world.
Not really. They kind of fell apart when faced with messy, fuzzy problems. Things like recognizing your cat in a photo or understanding what someone's saying. It's just too hard to write down all the rules for that kind of stuff.
Right. The world isn't just a neat set of if-then statements. So how did we get past that?
Well, that led to machine learning. The big shift was, instead of programming rules, let's have the algorithms learn from data.
Learning by example.
Precisely. And it's wild to think the very first ideas about computation, Lady Ada Lovelace, Charles Babbage, the analytical engine, way back in the 19th century. But the core machine learning idea is pretty intuitive. An algorithm looks at some input, tries to generate the output you expect, and then this is key. It measures how well it did, how far off it was.
Like adjusting your aim based on where the arrow landed?
Exactly. The source uses this nice picture of black and white dots, showing how the algorithm learns a boundary to separate them by seeing examples and getting feedback, mapping inputs to outputs, and measuring success.
Okay, learning from examples, adjusting based on mistakes. Got it. So what makes it deep learning?
Right, the deep part. Deep learning is a specific kind of machine learning that uses multiple stages, a deep sequence of simple data transformations. We call these stages layers.
Layers.
It sounds almost too simple, right? Just stacking simple steps. But the real power, the kind of surprising effectiveness, comes from stacking lots of these layers. It lets the network learn increasingly complex patterns.
So complexity emerges from many simple steps stacked together. What else is special about deep learning?
A huge, huge advantage is how it handles something called feature engineering.
Ah, I've heard that term. What is it exactly?
In older, shallow machine learning, humans, the experts, had to spend a ton of time figuring out the best way to represent the data for the algorithm. Like, if you're analyzing images, you look at edges, textures, colors. You had to handcraft these features.
So you had to tell the machine what parts of the data were important.
Exactly. Deep learning, though, automates this. The layers learn the relevant features directly from the raw data, all as part of the training process.
Yeah.
It learns the representation and the task simultaneously.
Wow, okay, so it simplifies the whole workflow quite a bit.
Massively. Instead of us needing to be data interpreters, we mainly focus on providing good data and setting up the learning process. The network does the heavy lifting of finding the patterns.
That sounds way more efficient, but why now? Deep learning ideas aren't brand new, are they?
No, not entirely.
Yeah.
But two really crucial things came together. First, massive leaps in computing power, specifically graphics processing units, GPUs.
From video games.
Yep. Initially driven by the gaming market for rendering realistic graphics.
Yeah.
But it turned out the architecture of GPUs, designed for doing lots of simple calculations in parallel, was perfect for the math involved in deep learning.
Huh. That's kind of funny. Gamers helping AI.
It's a great example of unexpected technological convergence.
Yeah.
I mean, the jump in power is staggering. A modern GPU can deliver way, way more teraflops. That's trillions of calculations per second than, say, the fastest supercomputers from the 90s.
So training these complex models suddenly went from taking months or years to
days or even hours in some cases. It just became feasible.
Okay, computing power was one key. What was the other?
Data. Just the sheer volume of data that became available. Think about the internet. billions of images, videos, vast amounts of text like Wikipedia.
Right, digital everything.
And deep learning models are data hungry. They need lots of examples to learn those complex patterns effectively. So you had this perfect storm. Powerful computation readily available and massive data sets to train on.
More processing power and much more data to process. Makes sense. Now, the source mentions progress following a sigmoid curve. What's that tell us?
Yeah, the S-curve idea. It suggests that after an initial period of really rapid, almost explosive progress, sort of the low-hanging fruit being picked, the rate of improvement might start to level off a bit.
So are we past the steepest part of the curve?
Well, the source was written a few years back, and it hinted we might be transitioning. We're definitely still making significant progress, don't get me wrong, but perhaps not at that same breakneck speed of the early 2010s. It's maturing.
Interesting perspective. Okay, so that's the high-level view. Let's dig into some of the core components. Tensors are mentioned right at the start as fundamental. What exactly are tensors?
Right, tensors. You can basically think of them as containers for data and deep learning. They're essentially multidimensional arrays of numbers.
Okay, like spreadsheets or lists.
Kind of, but they can have more dimensions.
Yeah.
So a single number, like just 5 foot, is a rank of 0 tensor, or a scalar. A list of numbers, like 1, 2, 3, that's a rank 1 tensor, or a vector.
Yeah.
A table of numbers, like a spreadsheet grid, that's a rank 2 tensor, a matrix.
Okay.
And you can keep going. A color image, for instance, can be represented as a rank 3 tensor, height, width, and then the color channels, red, green, blue.
And video.
Video adds a time dimension, so maybe rank 4 or even rank 5 if you have batches of videos. It's just a way to structure numerical data.
So it's all about organizing numbers in these multidimensional ways. What are the key properties of a tensor we need to know?
3 main things, usually.
Yeah.
First, the number of axes it has, that's its rank, or sometimes called endem in code. Second, its shape, which tells you how many dimensions it has along each axis. Like a 3x5 matrix has a shape of 3, 5.
Right.
And third, its data type, D-type, which specifies what kind of numbers are in it. Are they integers, floating point numbers, that sort of thing.
Rank, shape, data type. Got it.
Huh.
Now, the source calls tensor operations the gears of neural networks. What are these operations doing?
These are the fundamental ways the network manipulates the data flowing through it, the data held in those tensors. You have simple element-wise operations where you apply the same calculation like addition or multiplication to every single element in a tensor independently.
Okay, straightforward.
Enough, then there's something really important called broadcasting.
Broadcasting. What's that?
It's a clever way networks handle operations between tensors that don't have exactly the same shape. Instead of you needing to manually make them the same size, broadcasting sort of implicitly or virtually stretches the smaller tensor to match the larger one so the operation can happen.
So it avoids making lots of copies of data.
Exactly. It's super efficient. A common case is adding a vector to every row of a matrix, for example. Broadcasting handles that automatically.
Efficient data handling. What else?
The tensor product, or dot product, is absolutely fundamental. Geometrically, you can think of it as projecting one vector onto another, measuring how much they align. It's crucial for how layers transform data. And finally, tensor reshaping. This just changes the arrangement of dimensions of a tensor without changing the actual numbers or their order, like taking a long list and arranging it into a grid.
So manipulating these data containers, how does this connect to the idea of learning? The source talks about a geometric interpretation of deep learning. That sounds cool.
It's really the helpful way to think about it.
Yeah.
Imagine your raw input data, say, images of cats and dogs, as points scattered in some incredibly high dimensional space, maybe thousands of dimensions, one for each pixel.
Okay, a messy cloud of points.
Right. And initially, the cat points and dog points are all mixed up, like two crumpled sheets of colored paper, as the source puts it. A neural network, through all these layers and tensor operations, is essentially performing a very complex geometric transformation on this space.
A transformation.
Yeah, it's trying to warp and stretch the space in such a way that it uncrumples those sheets of paper. The goal is to transform the data so that the cat points end up in one region of the space and the dog points end up in another, cleanly separated.
Wow, okay. So it's learning a complex, uncrumpling process.
Exactly. Each layer performs a relatively simple step in this uncrumpling, maybe a rotation, a scaling, a translation, and crucially, a nonlinear twist.
The nonlinear part. That's where activation functions come in, right?
Absolutely critical. If you only had linear operations like dot products and additions, no matter how many layers you stacked, the whole network would still just be performing one big linear transformation. It couldn't learn complex curved boundaries.
It would be like trying to uncrumble paper using only stretching and rotating.
Pretty much. Activation functions, like the common ReLU function, introduce nonlinearities after each layer's linear transformation. They add the folding or twisting capability needed to learn those really complex patterns and separate the data effectively. They prevent the whole thing from collapsing into just a simple linear model.
Okay, so we're transforming data geometrically using tensors, operations, and these nonlinear activation functions. Now, the big question, how does the network learn the right transformations? The source calls gradient-based optimization the engine.
Right, this is the heart of the learning process. It starts with the concept of a derivative from calculus.
Okay, slope of a curve.
Basically, yeah. For a function, the derivative tells you how much the output changes for a tiny nudge in the input at any given point. It's the local steepness.
And how does that apply here?
Well, our network's operations are functions that take tensors in and spit tensors out. The derivative of a tensor operation is called the gradient. Think of it as a multidimensional derivative. It points in the direction of the steepest increase of the function's output.
Okay, a direction of steepest descent.
Exactly.
Hmm.
Now, how do we use this for learning? The main algorithm is stochastic gradient descent, or SGD.
SGD, heard of it. How does it work?
It's an iterative process. First, you grab a small, random batch of your training data, maybe a few images and their correct labels, cat or dog. Second, you feed that batch through your current network and calculate the loss. The loss is just a score that measures how wrong the network's predictions were for that batch. Higher loss means bigger mistakes.
So you see how bad it did on this little sample.
Yep. Third, and this is where the magic happens, you calculate the gradient of the loss with respect to the network's parameters, all those internal weights and biases in the layers.
Ah, so you figure out how changing each weight would affect the error.
Exactly. The gradient tells you for each weight which direction would make the loss increase the fastest.
So you want to go the opposite way.
Precisely. That's step 4. You nudge each weight slightly in the direction opposite to its gradient component. This downhill step should, on average, make the loss a little bit smaller for that batch.
Like rolling slightly downhill on an error landscape.
Perfect analogy.
Yeah.
And the size of that step you take is controlled by a parameter called the learning rate. You repeat this whole process, grab batch, calculate loss, compute gradient, update weights over and over again.
And gradually, the weights get better at minimizing the overall loss.
That's the goal. By repeatedly taking these small steps based on random batches, that's the stochastic part, the network hopefully converges toward the set of weights that performs well on the entire data set. Using batches rather than one sample at a time is called mini-batch SGD, which is standard practice.
Okay, that makes sense. What about backpropagation? Sounds complicated.
It sounds more intimidating than it is conceptually. Backpropagation is simply a very efficient algorithm for calculating all those gradients we just talked about, especially in deep networks with many layers.
So it's the how of calculating the gradient.
Exactly. It uses the chain rule from calculus to work backward from the final loss calculation, efficiently figuring out how much each weight in every layer contributed to that final error. It avoids redundant calculations. Think of it as an organized way to assign blame for the error back through the network.
Got it. An efficient blame assignment algorithm. And this whole forward pass, calculating loss, and backward pass, calculating gradients, can be visualized.
Yeah, often as a computation graph, which just shows the flow of tensors through the operations. It makes it clearer how the gradients are calculated by flowing backward through that same graph structure.
Okay, cool. I feel like I have a much better handle on the learning engine now. Let's talk tools. The source focuses heavily on Keras and TensorFlow. What role do they play?
Right. TensorFlow is the underlying engine, you could say. It's a huge, comprehensive, open-source platform for machine learning developed by Google. It provides all the low-level operations, tools for distributing computations, deploying models, the whole shebang. Think of it as a massive industrial workshop for ML.
Powerful, but maybe complex for everyday use.
It can be, yeah. And that's where Keras comes in. Keras is a high-level, very user-friendly deep learning API, also primarily developed at Google, that runs on top of TensorFlow and historically other backends too.
So Keras makes TensorFlow easier to use.
That's the main goal. Keras focuses heavily on developer experience, rapid prototyping, and ease of use. It lets you define models, layers, training procedures with much less code and complexity compared to using raw TensorFlow for everything. It's like having a set of really well-designed, intuitive power tools within that big TensorFlow workshop.
And it's popular. The source mentions huge adoption.
Oh, massively popular, both in research and industry. Google, Netflix, Uber, CERN, NASA, Yelp, Square, tons of places use Keras. Things you interact with daily, like YouTube recommendations or Waymo's self-driving tech, are often built with Keras models. It's also huge on Kaggle, the competitive ML platform.
Wow, okay. It's definitely a major player. So how do you actually build a model with Keras? The source mentions layers as the basic building blocks.
Exactly. You build Keras models by connecting together layers. Each layer represents a specific data transformation, like a dense layer, fully connected, convolutional layer for images, an RNN layer for sequences, and so on. Think of them like Lego bricks for neural networks.
So you pick the right bricks and stack them.
Pretty much. You typically define a sequence of layers, or, for more complex models, you use the functional API to create a graph of layers.
Okay, you assemble the layers into a model. What's next?
The compile step. This is crucial. Before you can train the model, you compile it, which means you configure the learning process. You tell Keras three main things.
Okay, what are they?
First, the loss function, how the model will measure its error during training. Second, the optimizer, the specific algorithm it will use to update its weights based on the loss, like SGD, or variations like Atom. And third, the metrics. These are just for monitoring, like accuracy, that you want to track during training but aren't directly optimized.
So compile sets the rules of the learning game, then you actually train it with fit.
Exactly. The fit method is where the training happens. You give it your training data, tell it how many times to go through the data, epochs, and importantly, you usually give it separate validation data.
Why the validation data?
The model trains on the training data, but after each epoch, it evaluates its performance on the validation data, which it doesn't train on. This lets you see how well the model is generalizing to unseen data and helps you spot overfitting early on.
Ah, okay. Monitoring generalization. And after training?
After fit is done, you use the predict method to get the model's predictions on new unseen data. That's the basic workflow. Define layers, assemble into a model, compile, fit, predict.
That seems pretty clear. Define, compile, fit, predict. Now, the source goes into some key practical concepts and terminology.
Yeah, it helps to be on the same page. A prediction is the model's output. The target is the true answer you wanted. In classification, you have classes, the categories, and a label is the correct class for one sample. Ground truth or annotations refer to all the correct labels for your dataset.
Okay. And different types of classification.
Right. Binary classification is 2 classes. Yes, and dog. Multi-class classification is more than 2, but only 1 is correct. For e.g., digit recognition 09. Multi-label classification means an input can belong to multiple classes simultaneously, e.g. tagging genres in a movie. And then scalar regression is predicting a single continuous number, not a class.
Like predicting a house price.
Exactly.
The source uses a movie review classification example with the IMDb dataset. What's the gist there?
It's a classic binary classification task. Is a review positive or negative? It illustrates the whole process. Load text data, convert words into numbers the network understands, like one-hot encoding or embeddings, split into training and validation sets, build a simple network, maybe some dense layers, ending with a sigmoid activation for a 0 to 1 probability, compile it using binary cross-entropy loss, and then fit it, watching the validation accuracy.
A concrete walkthrough of the steps. What's this information bottleneck idea?
Yeah. This can happen if you have intermediate layers in your network that are too small. They have too few units or dimensions. While sometimes forcing information through a bottleneck can encourage the network to learn compressed, essential representations, if the bottleneck is too tight, it might discard information crucial for the final task, limiting performance. It's a trade-off.
Finding the right amount of compression, and the house price prediction example highlights regression.
Yeah, the main differences there are, you're predicting a continuous value, price, so you'd use a different loss function suitable for measuring numerical error, like mean squared error, MSE. And the final layer typically wouldn't have an activation function like sigmoid, because you want it to output any real number, not just a probability between 0 and 1.
Different tasks, different loss, different output layer setup.
Got it. Now, the source really emphasizes that the ultimate goal is generalization. Why is that the absolute key? Because that's what makes a model useful. Generalization is the model's ability to perform well on new, unseen data that it wasn't explicitly trained on. If a model just memorizes the training data perfectly but fails miserably on anything new, it hasn't actually learned the underlying patterns. It's useless in the real world.
It needs to work beyond the textbook examples. How does deep learning achieve this? The manifold hypothesis comes up.
Right. This is a really interesting idea. It suggests that even though real-world data, like images, might seem to live in a space with a huge number of dimensions, all the pixels, the actual data points tend to lie on or close to a much lower dimensional, smoother surface or manifold embedded within that high-dimensional space.
So the data isn't just randomly scattered everywhere, it has some hidden structure.
Exactly. Think of all possible combinations of pixel values. Most of them don't look like real images at all. The image manifold is the subset that corresponds to plausible images. A well-trained deep learning model effectively learns an approximation of this underlying manifold.
And how does that help generalization?
When the model sees a new data point that's close to the manifold it learned, it can often make a good prediction by essentially interpolating based on the nearby points it did see during training. It's learned the rules or the structure of the data space.
So it's finding the hidden patterns or surfaces in the data? What properties of deep learning models help them do this?
Their learned transformations tend to be smooth and continuous, partly because the operations are differentiable. We can calculate gradients. This means small changes in the input usually lead to small changes in the output, which helps the model interpolate well between training examples and generalize to nearby unseen points.
Smoothness helps interpolation.
Okay.
The source also describes this journey, starting random, potentially overfitting, and finding a robust fit in the middle. Can you walk through that?
Sure. When you start training, the model's weights are random, and it performs poorly. As it sees data and updates weights via SGD, its performance on both the training data and the validation data improves. This is the learning phase. But if you train for too long, especially with a powerful model, it can start to fit the training data too well. It begins memorizing the specific examples, including any noise or irrelevant details. This is overfitting.
And how do you know it's happening?
You'll see the training loss keep going down, but the validation loss, the error on unseen data, will start to increase. The model is getting better at the training set, but worse at generalizing. The sweet spot, the robust fit, is usually around the point where the validation loss is at its minimum, just before it starts to rise again.
Finding that balance point before memorization takes over. So how do we reliably measure this generalization performance? The source mentions different evaluation protocols.
Yeah, having a trustworthy way to evaluate is crucial. The simplest is simple holdout validation. You just split your data once, training set, validation set for tuning and monitoring, and a final test set used only once at the very end for the final score.
But what if you don't have much data?
Right, that's the limitation. If your validation test sets are small, your evaluation might not be very reliable. It could just be luck whether the model does well on that specific small slice. So for smaller data sets, we use cross-validation, like k-fold validation.
K-fold.
You split the data into k equal parts, or folds. Then you train k separate models. Each model uses k1 folds for training and the remaining 1 fold for validation. You average the validation scores across all k runs to get a more robust estimate of performance.
So you use all the data for both training and validation eventually?
Exactly, just in different combinations. And iterated k-fold validation takes it even further. You repeat the whole k-fold process multiple times, shuffling the data differently each time, and average the results. That gives you an even more stable evaluation, reducing the impact of how the data happen to be split.
More robust evaluation, especially with limited data. Now, for improving model fit, the source suggests a strategy. First, aim to overfit. That sounds wrong.
It does seem counterintuitive, doesn't it? But the logic is, before you worry about preventing overfitting, improving generalization, you need to make sure your model is actually capable of learning the task in the first place.
You need enough engine power.
Exactly. If your model's too simple, it might not even be able to fit the training data well. This is called underfitting. So the first step is often to make your model powerful enough. For example, add layers or units so that it can achieve low error on the training set, even if that means overfitting initially.
Prove it can learn the training data, then worry about making it generalized.
Precisely. Once you've established you have sufficient model capacity, because you can overfit, then you start applying techniques to regularize the model and fight that overfitting to improve its performance on unseen data.
Okay, that makes more sense. And how do you typically increase model capacity to achieve that initial fit?
Usually by making the network larger or wider. You can add more layers, making it deeper, or increase the number of neurons or filters in existing layers, making them wider. A bigger model has more parameters, more flexibility to learn complex patterns, which helps it fit the training data, but also makes it more prone to overfitting if unchecked.
More knobs to turn, basically. So once we can overfit, we need to dial it back. That's where regularization techniques come in.
Exactly. Regularization refers to any method added to the learning process to specifically combat overfitting and improve generalization. The goal is to make the model simpler or more robust in some way.
What are some common regularization methods?
The source mentions a couple of key ones. Weight regularization, like L1 and L2 regularization, also called weight decay, adds a penalty to the loss function based on the size of the model's weights. This encourages the network to learn smaller, simpler weight configurations, which often generalize better.
Penalizing complexity.
Kind of, yeah. Another really popular and effective one is dropout.
Dropout, what does that do?
During training, dropout randomly sets the output of a fraction of the neurons in a layer to 0 for each training sample.
It just switches them off randomly?
Temporarily, yes, for that specific sample pass. It forces the network to not rely too heavily on any single neuron or small set of neurons, making it learn more redundant and robust representations. It's like training different, slightly smaller networks within the main network constantly.
Interesting, like forcing teamwork by occasionally making some players sit out. Okay, the source then briefly outlines a universal workflow of machine learning. What are the key stages?
It's a good general framework. 1, define the problem clearly. What are you predicting? Why? 2, collect and prepare your data. Clean it, label it. 3, choose how you'll measure success. Accuracy, MSE, something else. 4, develop the model. This involves preparing data specifically for the model, choosing an evaluation protocol like holdout or k-fold, building the actual model architecture, and training tuning it. 5, deploy the model and monitor it in the real world.
Define, collect, measure, develop, deploy. A logical flow. And speaking of data, the source really hammers home its importance, calling it the unreasonable effectiveness of data.
Yeah, this is a crucial point often overlooked by beginners focusing only on algorithms. The idea is that often getting more high-quality relevant data will improve your model's performance far more than fiddling endlessly with the model architecture itself. A decent model with great data often beats a state-of-the-art model with mediocre data.
So data can be king.
In many, many cases, yes. Investing in data collection, cleaning, and careful annotation, labeling, is often the highest leverage activity in an ML project, though annotation can be super labor-intensive and requires a careful process itself.
Right. What about dealing with messy real-world data, like missing values?
Very common problem. You definitely want to avoid just plugging in arbitrary values like 0, as that can confuse the model. For numerical features, imputing the mean or median of the column is often a reasonable start. For categorical features, maybe create a special missing category. Sometimes more advanced imputation methods are needed, or you might even train the model to explicitly handle missingness by, say, adding a feature indicating whether the original value was missing.
Handling the gaps intelligently, and the source mentions leveraging existing work.
Absolutely. For many common problems, there are well-established architectures and approaches. Don't reinvent the wheel if you don't have to. Look for prior art and existing templates.
Okay, we've trained a model, it looks good, now we need to deploy it. What are the common ways to do that?
Several ways, depending on the use case. A very common one is serving it via a REST API. Your trained model lives on a server, and other applications send it data, like an image or text, via a web request, and the model sends back its prediction.
Like a prediction service online.
Exactly. You can host this yourself or use cloud platforms like Google Cloud AI Platform, AWS SageMaker, Azure ML, which handles scaling, management, etc. This is great for web services, back-end processing like fraud detection, recommendations.
What about running it directly on a user's device?
Yep, that's another option. Using TensorFlow.js, you can run models directly in a web browser or in desktop apps built with web technologies. And for mobile apps or embedded systems, like smart devices, there's TensorFlow Lite.
Light implies smaller, faster.
Usually, yes. Deploying to mobile or embedded often requires inference model optimization to make the model smaller and run faster with less power consumption.
What kind of optimizations are we talking about?
Two main techniques mentioned are weight pruning, which involves removing connections, weights in the network that are deemed less important, essentially making the network sparser, and quantization, which reduces the numerical precision of the weights, for example, using 8-bit integers instead of 32-bit floating point numbers. Both can significantly shrink the model size and speed up computations, often with only a small hit to accuracy.
Trimming the fat and reducing precision. And once deployed, we need to keep an eye on it.
Absolutely critical. Monitoring deployed models is essential. The real world changes, data distributions shift, data drift, and a model's performance can degrade over time. You need systems to track key metrics, maybe perform periodic manual audits on live predictions, or use user feedback to catch when things go wrong.
Constant vigilance. Okay, going back to building models in Keras, the source mentions 3 APIs: sequential, functional, and subclassing. Quick comparison.
Sure. The sequential API is the simplest, just a linear stack of layers. Model.add-layer, great for straightforward architectures.
Easy start.
The functional API is more flexible. It lets you build models like graphs with multiple inputs, multiple outputs, shared layers, branches. Much more versatile for complex designs. You define how layers connect explicitly.
More power for complex stuff.
And model subclassing is the most low-level and flexible. You define your model by subclassing the Keras, model class, and implementing the forward pass call method yourself. It gives you full control, but requires more code. It's great for research or highly customized models.
Sequential for simple stacks, functional for graphs, subclassing for full control.
Got it. And the functional API enables those multi-input and multi-output models.
Exactly. Imagine a model that takes a user's profile info and their recent browsing history to predict both what product category they might like and how much they might spend. The functional API makes defining that kind of complex input-output structure quite natural.
Very flexible. What about callbacks in Keras? What do they do?
Callbacks are super useful tools you can plug into the fit process. They are objects that can perform actions at various stages of training, like at the beginning or end of an epoch or a batch.
Like little automated helpers. Yeah. Examples include early stopping, which monitors a validation metric like loss or accuracy, and stops training automatically if it stops improving, preventing overfitting and saving time. Model checkpoint saves your model periodically during training, usually keeping only the best version found so far based on the validation metric.
So you don't lose your best model if training goes on too long.
Right. And you can write custom callbacks for almost anything, logging extra information, adjusting the learning rate dynamically, visualizing things. Keras' integration with TensorBoard for visualizing training progress also uses callbacks.
Handy tools for managing training. For even more control, the source mentions writing custom training loops. Why do that instead of just using fit?
Fit is great and covers maybe 95% of use cases. But sometimes you need finer control than fit allows. Maybe you're implementing a very non-standard training procedure like certain types of reinforcement learning or Jan training, or you need very specific gradient manipulations.
When the standard way isn't enough.
Exactly. In these cases, you can write the training loop yourself in Python. You typically use TensorFlow's TF gradient tape context to watch the computations in the forward pass, then explicitly calculate gradients of the loss with respect to the model's weights, and finally apply those gradients using an optimizer instance.
More manual work, but total control.
Yes. And you can still use Keras metrics within these custom loops. For performance, you often wrap your training step function in tf.function, which compiles the Python code into a highly optimized TensorFlow graph.
Trade-off between convenience and control performance. Okay, let's shift gears to a common practical challenge. Working with small data sets, especially in computer vision. Deep learning needs lots of data, right?
Typically, yes, especially when training large models from scratch. So small data sets present a real challenge. The source outlines 3 main strategies.
What are they?
1, you could try training a relatively small, simple model from scratch, hoping it doesn't have enough capacity to overfit badly. 2, use a pre-trained model for feature extraction. 3, use a pre-trained model and fine-tune it. And almost always, you'll want to use data augmentation.
Let's unpack those. Data augmentation first.
This is crucial for small image datasets. It means artificially increasing the size of your training set by creating modified copies of your existing images. You apply random transformations like zooming, rotating, shearing, flipping horizontally. This teaches the model that these variations don't change the object's identity. A slightly rotated cat is still a cat and makes it more robust.
Generating more examples from the ones you have.
Exactly. Keras has layers that can do this on the fly during training.
Okay, now feature extraction versus fine-tuning using pre-trained models.
Right. So a pre-trained model, like one trained on the huge ImageNet dataset, has already learned powerful visual features in its lower layers. For feature extraction, You take this pre-trained model, chop off its final classification layer, freeze all the remaining weights so they don't change, and then add your own new small classifier on top. You only train this new classifier on your small data set using the powerful frozen features extracted by the pre-trained base.
Leveraging the pre-trained knowledge without changing it.
Yes. Fine-tuning goes a step further. You start similarly, maybe even do some feature extraction training first, but then you unfreeze some of the top layers of the pre-trained base model and continue training both those unfrozen base layers and your new classifier, usually with a very low learning rate.
So you let the pre-trained model adapt slightly to your specific data.
Exactly. It allows the high-level features learned on ImageNet to be slightly adjusted for the nuances of your particular task. It often yields better results than pure feature extraction, but requires more care, like using a tiny learning rate, to avoid destroying the valuable pre-trained weights. Sometimes you need to be careful about unfreezing certain layer types, like batch normalization.
Two powerful ways to leverage existing knowledge for small data sets. Now, how do we understand what these convolutional neural networks are actually learning inside? They seem like black boxes.
They can feel that way, but there are techniques to peek inside. One is visualizing intermediate activations or feature maps. You feed an image into the network and look at the output of various layers. You can often see how early layers detect simple things like edges or textures, while deeper layers combine those to respond to more complex patterns or object parts.
Seeing the features emerge layer by layer.
Yeah. Another technique is visualizing convet filters. Here, you try to find or generate an input image pattern that maximally activates a specific filter in a layer. This gives you an idea of the visual pattern that filter is tuned to detect.
What the filter is looking for.
Right. And a third very useful technique is visualizing heat maps of class activation, often using methods like GradCam. This produces a heat map overlaid on the input image, showing which parts of the image were most important for the network's decision to classify it as a particular class. Like, if it classifies an image as cat, the heat map might highlight the cat's face and ears.
Pinpointing the evidence in the image. Cool. The source then briefly touches on deep learning for time series. What's special here?
Time series, data weather, stock prices, sensor readings, has that crucial temporal order. Past values influence future values. There are trends, seasonality, dependencies over time. Standard feed-forward networks don't handle this sequence aspect well.
So we need models that understand sequence and time.
Exactly. That's where recurrent neural networks, RNNs, come in. An RNN processes sequence data step by step. And crucially, it maintains an internal state or memory that carries information from previous steps to influence the processing of the current step. It's like having a loop where the output from the previous time step feeds back into the computation for the current time step.
They have memory of the past.
Essentially, yes. Basic RNNs can struggle with long-range dependencies, though. So more advanced variants like LSTM, long short-term memory, and GRU, gated recurrent unit, were developed. They use internal gates to better control what information is stored, forgotten, or passed through, allowing them to capture patterns over longer timescales.
LSTM and GRU are the workhorses for sequences.
Very much so. The source also mentions that applying dropout correctly in RNNs is a bit different. You need to use consistent dropout masks across time steps.
Yeah.
And that bidirectional RNNs, which process the sequence both forwards and backwards, can sometimes improve performance by giving the network context from both past and future.
Handling time and sequence. What about deep learning for text? Language is sequential too, but also very complex.
Absolutely. A key first step is representing text numerically. Tokenization breaks text into units, words, subwords. Then you need to convert these tokens into vectors. One hot encoding is one way, sparse, very high dimensional. More powerful are word embeddings, which learn dense, lower dimensional vectors where words with similar meanings have similar vector representations.
Capturing meaning in the vectors.
Yes. Keras' text vectorization layer can handle a lot of this pre-processing. Tokenization, building a vocabulary, converting to vectors, quite easily, even directly within the model.
Okay, once we have vectors, how do we model sequences of words?
Two main families of approaches. Bag of words models ignore word order and just look at which words or pairs enneagrams are present. Simple, fast, but loses sequential information.
Order doesn't matter.
Right. Then you have sequence models that do consider word order. RNNs, LSTM, GRU, were dominant here for a while. More recently, the transformer architecture has become incredibly successful, especially for large language models.
Transformers, what's their key idea?
The core mechanism is self-attention. It allows the model, when processing a word, to look at all other words in the sequence and dynamically weigh how relevant each of them is for understanding the current word in context. It's incredibly powerful for capturing long-range dependencies. Multi-head attention lets it do this from different perspectives simultaneously. For tasks like translation, sequence-to-sequence models, often built with RNNs or transformers, learn to map an input sequence to an output sequence.
Attention lets it focus on relevant parts of the sequence. Okay, one more area. Generative deep learning. This sounds different.
It is. Instead of classifying or predicting based on input data, generative models learn the underlying distribution of the training data so well that they can create new data samples that look like they could have come from the original data set.
Creating new images, text, etc.
Exactly. RNNs can be used for sequence generation, like generating text character by character. Deep Dream was an early fun example using convets to generate trippy, dreamlike images by amplifying patterns the network saw. Neural style transfer combines the content of one image with the artistic style of another.
Mixing content and style.
Yeah. Then you have more structured generative models like variational autoencoders, VAEs, which learn a compressed latent space from which you can sample points and decode them into new data instances. And generative adversarial networks, GANs, which involve a clever competition between a generator network trying to create realistic data and a discriminator network trying to tell real from fake. This forces the generator to get incredibly good.
The generator versus the critic. Sounds fascinating. Okay, wrapping up, the source gives tips on getting the most out of your models and reflects on limitations and the future. Any key takeaways there?
For maximizing performance, hyperparameter optimization, systematically searching to the best model architecture settings, learning rate, etc. is important. Tools like Keras can automate this, though you need to be careful not to overfit your validation set during this process.
Tuning the knobs automatically.
Right. And for large models, scaling up training becomes key. Using mixed precision, lower precision numbers for faster math on GPUs, distributing training across multiple GPUs or even TPUs, tensor processing units, in the cloud are common strategies. It's all about enabling that iterative loop. Idea, experiment, result, new idea.
Speeding up the experimentation cycle and the limitations.
Crucially, the source warns against anthropomorphizing these models. They are amazing pattern matchers, but they don't understand in the human sense. They can be brittle, failing unexpectedly on inputs slightly different from the training data. They are more like incredibly sophisticated automatons than truly intelligent agents capable of robust reasoning or generalization to truly novel situations.
Understanding the difference between pattern matching and real understanding.
Exactly. The future might involve bridging the gap between deep learning's strength in perception intuition, value-centric abstraction, and more traditional symbolic AI's strength in reasoning and structure, program-centric abstraction, maybe augmenting neural nets with programming-like primitives. Multitask learning is also promising. And while AGI, artificial general intelligence, is the long-term dream for some, we should have realistic expectations about current capabilities. The keen advice: keep learning. The field moves incredibly fast.
Continuous learning is essential. Some really important final thoughts there on capabilities and future directions.
So to quickly recap our deep dive today, we've gone from defining deep learning within AI through its core components like tensors and gradient descent, explored practical tools like Keras and TensorFlow, discussed the critical goal of generalization and how to achieve it, touched on applications in vision, time series, text, and even generation.
Yeah, we covered a lot of ground, and hopefully we did it in a way that gives you, the listener, a really solid, engaging grasp based on the source material, Deep Learning with Python, without getting totally lost in the weeds. I know I learned a few things.
Absolutely. We hope you found some parts surprising, maybe sparked some ideas about how this technology works and where it might be applied. It's a complex field, but the core ideas are actually quite elegant when you break them down.
Definitely. And this is really just scratching the surface, isn't it? If specific areas like GANs or transformers or fine-tuning caught your interest, there's so much more to explore.
For sure. Consider this your foundation.
That's the value of taking a deep dive, getting that solid foundation quickly and thoroughly. Thanks so much for joining us today.